Hello everyone and welcome to our new YouTube course, Thermodynamics and Kinetics of Materials. I'm thrilled to have you join me on this fascinating journey into the very heart of how materials interact, behave, and transform. In this first lesson, lesson 1.1, we are going to lay the groundwork. We'll answer the fundamental question: what exactly is thermodynamics in the context of materials science? And then we'll dive into some essential, basic concepts and definitions that will be our building blocks for the entire course. So let's start with the big one. What is thermodynamics? The word itself comes from Greek therme, meaning heat, and dynamics, meaning power or force. At its core, thermodynamics is the science that deals with heat and its relation to other forms of energy and work. It's about how energy is transferred and transformed, and crucially, it helps us understand the feasibility and spontaneity of processes. Now, why is this so incredibly important for material scientists and engineers? Well, think about it. Why does a steel harden when you quench it? Why do some materials corrode while others don't? How do we design alloys that are stable at high temperatures? What drives the phase transformation from one crystal structure to another? The answers to these questions and countless others lie squarely in the principles of thermodynamics. It's the framework that allows us to predict materials stability, phase transformations, and chemical reactions. For materials stability, will a certain material phase exist under specific conditions? For phase transformations, when and how will a material change from one state to another, like liquid to solid, or one crystal structure to another? For chemical reactions, will two materials react and what will be the driving force for that reaction? Essentially, thermodynamics tells us what can happen. It defines the limits and possibilities for materials' behavior. To speak the language of thermodynamics, we need to establish some common terms. Let's begin with the fundamental idea of a system, surroundings, and boundary. Is that true? Imagine you're studying a small piece of a metal. That piece of a metal is your system. It's the specific part of the universe that we choose to study. Everything outside that piece of metal, the air around it, the furnace it's in, the room, that is the surroundings. The imaginary or real line separating your system from its surroundings is the boundary. Based on how the system interacts with its surroundings, we classify them as an open system, closed system, an isolated system. An open system can exchange both energy, like heat and matter, with its surroundings. Think of a molten metal bath in a furnace where gases are coming off. A closed system can exchange energy but not matter. A sealed container of gas being heated is a closed system. An isolated system exchanges neither energy nor matter. A perfectly insulated thermos flask is an approximation of an isolated system. You're listening, right? Next, let's talk about properties. These are characteristics of our system. We categorize them into two types, extensive and intensive. Extensive properties depend on the amount of matter in the system. Examples include mass, volume, and total energy. If you double the amount of material, you double its mass. Intensive properties are independent of the matter. Think of temperature, pressure, and density. A small piece of iron and a large block of iron at the same temperature will both have the same temperature. Pay attention. This is a crucial distinction: state function versus path functions. A state function or property depends only on the initial and final states of the system, not on the path taken to get there. Imagine climbing a mountain. Your change in elevation from base camp to the summit is a state function. It doesn't matter if you took the winding trail or the direct steep path. Examples in thermodynamics include internal energy, enthalpy, entropy, and Gibbs free energy. A path function, on the other hand, does depend on the path taken. The amount of work you do climbing that mountain or the heat generated would be path function. For us, the most common path functions are heat, Q, and work, W. One of the most important concepts in thermodynamics is equilibrium. A system is in equilibrium when there are no driving forces for change. We often talk about different types of equilibrium: thermal, mechanical, chemical. Thermal equilibrium is when there is no temperature difference within the system or between the system and its surroundings, no net heat flow. Mechanical equilibrium is when there are no unbalanced forces within the system or between the system and its surroundings, no net work being done. Chemical equilibrium is when there is no tendency for the chemical composition of the system to change. The rates of forward and reverse reactions are equal. When a materials system reaches equilibrium, it is in its most stable state under the given conditions. Finally, let's quickly define some common processes we'll encounter. Isothermal process. Isothermal process occurs at constant temperature. Finally, let's quickly define some common processes we'll encounter. Isothermal, isobaric, isochoric, adiabatic. Isothermal process occurs at constant temperature. Think of a material being slowly heated in a large, well-regulated furnace. Isobaric process occurs at constant pressure. Many metallurgical processes like casting open to the atmosphere happen at constant atmospheric pressure. Isochoric process occurs at constant volume, heating a gas in a rigid sealed container. Adiabatic process, no heat is exchanged. No heat is exchanged, Q equals to 0 with the surroundings. This often happens in a very fast processes where there isn't time for heat transfer or in perfectly insulated systems. So there you have it, a foundational introduction to thermodynamics and the key terms we'll be using throughout this course. We've covered what thermodynamics is and why it's vital for understanding materials, the concepts of systems, surroundings, and boundaries, the difference between extensive and intensive properties, the critical distinction between state functions and path functions, the various types of equilibrium, and common thermodynamic processes. This vocabulary will be essential as we move forward. In our next lesson, we'll dive into the very first pillar of thermodynamics, the first law of thermodynamics, or the law of conservation of energy. Don't forget to like this video, subscribe to the channel, and hit that notification bell so you don't miss any future lessons. If you have any questions, drop them in the comments below. Thanks for watching, and I'll see you in the next lesson. We are taking a monumental step forward as we dive into the very first pillar of thermodynamics, the first law of thermodynamics. This law is also famously known as the law of conservation of energy. It's a concept you've likely encountered before, but we'll explore its profound implications specifically for materials systems. We'll break down its statement, understand its components like internal energy, heat, and work, and then introduce a crucial concept, enthalpy. Finally, we'll look at some real-world applications in materials engineering. Let's get straight to the heart of it. The first law of thermodynamics can be stated in many ways, but for a closed system, it's most commonly expressed as delta U equals Q minus W. Let's unpack this equation. Delta U represents the change in the internal energy of the system. Internal energy U is a state function. It encompasses all energy within the system at a microscopic level, the kinetic and potential energies of its atoms and molecules. It includes translational, rotational, vibrational energies, and even electronic and nuclear energies. Q represents the heat transferred to the system. If heat is added to the system, Q is positive. If heat leaves the system, Q is negative. W represents the work done by the system on its surroundings. If the system does work, for example, expand against an external pressure, W is positive. If work is done on the system, for example, compression, W is negative. So what does this equation tell us? It says that the change in a system's internal energy is equal to the heat added to the system minus the work done by the system. In simpler terms, energy cannot be created or destroyed. It can only be transformed from one form to another or transferred from one place to another. Think of it like a bank account for energy. Any deposit, heat added, or withdrawal work done by the system directly affect the balance, internal energy. While internal energy U is fundamental, another thermodynamic property, enthalpy, is incredibly useful, especially in materials science. Why? Because many processes in materials engineering, like melting, solidification, or chemical reactions, occur at constant pressure, often atmospheric pressure. Enthalpy is defined as H equals U plus PV, where U is the internal energy, P is the pressure of the system, V is the volume of the system. Like internal energy, enthalpy is also a state function. The change in enthalpy, delta H, for a process occurring at constant pressure is equal to the heat absorbed or released by the system. Delta HQP at constant pressure with indices P referring to being cut at constant pressure. This makes enthalpy a very practical quantity. When you measure the heat released during a combustion reaction or the heat required to melt a metal, you're often measuring the change in enthalpy. We also talk about heat capacity, CAP heat capacity at constant pressure. The amount of heat required to raise the temperature of a substance by 1 degree Celsius or Kelvin at constant pressure. CAV, heat capacity at constant volume. The amount of heat required to raise the temperature of a substance by 1 degree Celsius or Kelvin at constant volume. For solids and liquids, CAP and CAV are very similar, but for gases, the difference can be significant. Just stay right here. Now let's bring the first law and enthalpy into the realm of material science with some practical applications. These applications being energy changes during phase transitions, heat of formation of compounds, energy balance in metallurgical processes. For energy changes during phase transitions, consider melting. When you melt a solid, you are adding heat. This heat doesn't immediately raise the temperature. Instead, it goes into breaking the bonds in the solid lattice to form a liquid. This is the latent heat of fusion, which is essentially an enthalpy change delta H fusion. Similarly, boiling involves the latent heat of vaporization. These are critical for understanding casting, welding, and heat treatment processes. For the second application, I'm mentioning heat of formation of compounds. When elements combine to form a compound, for example, iron reacting with oxygen to form iron oxide, energy is either released or absorbed. The standard enthalpy of formation delta HF naught tells us the heat change when 1 mole of a compound is formed from its constituent elements in their standard states. This value is crucial for predicting the energy balance of chemical reactions in metallurgy and ceramics. Energy balance in metallurgical processes is a number 3 practical application I'm talking about when gathering the first law and enthalpy. Think about a blast furnace, where iron ore is reduced to molten iron. This is a massive chemical reactor. The first law allows engineers to perform an energy balance in the furnace. They can account for the energy input, energy output, and heat losses, for the energy input from coal and natural gas, for the energy output, molten metal, slag, hot gases. This helps optimize the process for efficiency and safety. Similarly, in heat treatment processes like annealing or quenching, understanding the heat transfer Q and internal energy changes delta U within the material is vital to achieve desired microstructure and properties. So to summarize, the first law of thermodynamics, delta U equals Q minus W, is a fundamental statement of energy conservation. It teaches us that energy is always accounted for. We also introduced enthalpy, H equals U plus PV, which is particularly useful for processes occurring at constant pressure, like many in materials processing. Understanding these concepts allows us to quantify energy changes in material systems, from phase transformations to chemical reactions, and to design more efficient industrial processes. For those of you who want to dive deeper, I recommend checking out these references. In our next lesson, we'll tackle the second law of thermodynamics, which introduces the concept of entropy and helps us understand the direction and spontaneity of processes. Don't forget to like this video, subscribe to the channel, and hit that notification bell so you don't miss any future lessons. If you have any questions, drop them in the comments below. Thanks for watching, and I'll see you in the next lesson. We learned that energy cannot be created or destroyed, only transformed. But the first law doesn't tell us why processes happen in a certain direction or if they will happen at all. It doesn't explain why heat flows from hot to cold, or why a dropped glass shatters, but doesn't spontaneously resemble itself. That's where the second law of thermodynamics comes in. This law is perhaps the most profound and far-reaching of all thermodynamics principles. It introduces the concept of entropy and provides the critical insight into spontaneity and the direction of natural processes. We'll explore its various statements, delve deep into what entropy truly represents, and then see its powerful application in understanding materials systems. The second law of thermodynamics can be stated in several equivalent ways. Let's look at two of the most common. First, the Clausius statement. It's impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a cooler body to a hotter body. What does this mean? It simply means that heat spontaneously flows from a hotter object to a colder object, never the other way around, without external work being done. You don't see ice cubes spontaneously heating up a room by getting colder themselves. This is a direct consequence of the second law. Second, the Kelvin-Planck statement. It's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. This statement highlights the impossibility of a perpetual motion machine of the second kind. You don't convert 100% of a heat into work in a cyclic process. There will always be some heat rejected to a lower temperature reservoir. This is why heat engines like those in power plants always have an exhaust. Both statements point to the fundamental concept of irreversibility and the directionality of natural processes. Now let's introduce the core concept associated with the second law, entropy. Entropy is a state function, just like internal energy and enthalpy. Its change, dS, is defined as dS equals dq rev over T, where dq rev is an infinitesimal amount of heat transferred during a reversible process. T is the absolute temperature at which the transfer occurs. But what is entropy intuitively? While its mathematical definition relates to reversible heat transfer, a more conceptual understanding is that entropy is a measure of the disorder, randomness, or dispersal of energy within a system. Think about it. When you drop a perfectly ordered stack of coins, when a gas expands into a vacuum, when ice melts into water, when you drop a perfectly ordered stack of coins, they are scattered into a disordered arrangement. This is an increase in entropy. When a gas expands into a vacuum, its molecules become more dispersed, leading to an increase in entropy. When ice melts into water, the molecules gain more freedom of movement, increasing entropy. The second law, in its most general form, states that for any spontaneous process, the total entropy of an isolated system or their universe always increases. If a process leads to a decrease in total entropy, it's impossible. If the total entropy remains constant, the process is reversible and at equilibrium. Entropy change in reversible with irreversible process. For a reversible process, delta S of system plus delta S of surroundings equals 0. For an irreversible spontaneous process, delta S of system plus delta S of surroundings is greater than 0. This means that While the entropy of a system can decrease, for example, water freezing into ice, it can only do so if the entropy of the surroundings increase by a greater amount, ensuring the total entropy of the universe still increases. The second law and the concept of entropy have profound implications for materials science, predicting the spontaneity of reactions and phase transformations. The second law provides the ultimate criterion for spontaneity. A process will occur spontaneously if it leads to an overall increase in the entropy of the universe. This is a powerful tool for predicting whether a certain chemical reaction will proceed or if a phase transformation will naturally occur under given conditions. For instance, why does a supersaturated solid solution precipitate a new phase? Because the overall entropy of the system and surroundings increases. The next implication we are announcing here is entropy of mixing in alloys. When you mix two different types of atoms to form an alloy, the system becomes more disordered compared to the pure elements. This leads to a positive entropy of mixing, delta S of mix. This positive entropy of mixing is a significant driving force for the formation of solid solutions in alloys, even if the enthalpy of mixing is slightly unfavorable. It explains why many alloys exist. And the next application is the entropy considerations in defect formation. Materials are rarely perfect. They contain defects like vacancies, missing atoms, or interstitial atoms. While creating a vacancy requires energy and enthalpy penalty, it also increases the local disorder and thus the entropy of the crystal. At finite temperatures, the entropy gain associated with creating these defects often outweighs the enthalpy cost, leading to an equilibrium concentration of defects in materials. This is crucial for understanding diffusion, creep, and many other material properties. So to recap, the second law of thermodynamics is the compass that guides us in understanding the direction and spontaneity of natural processes. It introduces entropy, a measure of disorder, and states that for any spontaneous process, the total entropy of the universe always increases. This law is indispensable for materials scientists, allowing us to predict whether a reaction or phase transformation is feasible, understand the driving forces behind alloy formation, explain the presence and behavior of defects in crystalline materials. To delve deeper into the second law and entropy, I highly recommend these references. And in our next lesson, we'll briefly touch upon the third law of thermodynamics, and then we'll combine all these laws with the concept of free energy to create powerful tools for materials analysis. Don't forget to like this video, subscribe to the channel, and hit the notification bell so you don't miss any future lessons. If you have any questions, drop them in the comments below. Thanks for watching, and I'll see you in the next lesson. In our previous lessons, we've explored the first law of thermodynamics, the conservation of energy, and the second law, which introduced the crucial concept of entropy and the direction of a spontaneous process. Now, we'll briefly cover the final piece of the puzzle, the third law of thermodynamics. While the first and second laws deal with changes in energy and entropy, the third law provides a crucial reference point, allowing us to determine absolute values of entropy. The third law of thermodynamics can be stated as the entropy of a perfect crystalline substance is zero at absolute zero temperature or 0 Kelvin. Let's break this down. Perfect crystalline substance. This refers to a material where all atoms or molecules are arranged in a perfectly ordered, repeating pattern with no defects, impurities, or disorder. Absolute zero temperature or 0 Kelvin. This is the theoretical lowest possible temperature where all atomic and molecular motion ceases and particles are in their lowest possible energy state. So at 0 Kelvin in a perfectly ordered crystal, there is no thermal motion, no positional disorder, and no vibrational energy. Therefore, the disorder or entropy is at its absolute minimum, 0. So when all atomic and molecular motion ceases, the entropy is at its absolute minimum. Here we are going to highlight the significance of the third law. Why is this law significant for us in material science? The first significance: establishing absolute entropy values. Unlike internal energy or enthalpy, for which we typically calculate changes delta U and delta H, the third law provides a basis for calculating absolute entropy values for substances at any given temperature. By integrating the heat capacity data from 0 Kelvin up to a desired temperature, we can determine the standard absolute entropy S0 of a substance. This is incredibly useful for thermodynamic calculations, especially when dealing with chemical reactions and phase equilibria. The next significance to be mentioned is predicting feasibility and equilibrium. Having absolute entropy values allows us to calculate the absolute Gibbs free energy of substances, which, as we'll see in the next lesson, is the ultimate criterion for predicting the spontaneity and equilibrium of processes in materials systems. Without the third law, we would only be able to calculate changes in free energy, not absolute values. In a sense, the third law of thermodynamics provides the anchor for our entropy scale, stating that a perfectly ordered crystal has zero entropy at absolute zero. This allows us to determine absolute entropy values for materials, which are indispensable for comprehensive thermodynamics analysis. For a more detailed discussion on the third law, you can refer to this reference. Now that we've covered all three fundamental laws, we have all the tools to introduce the incredibly powerful concept of free energy in our next lesson. This is where we truly combine the first and second laws to predict the direction and extent of reactions and transformations in materials. Don't forget to like this video, subscribe to the channel, and hit that notification bell so you don't miss any future lessons. If you have any questions, drop them in the comments below. Thanks for watching, and I'll see you in the next lesson. We've now covered the three fundamental laws of thermodynamics. The first law on energy conservation, the second law on entropy and spontaneity, and the third law which sets the absolute zero for entropy. Each law gives us a piece of the puzzle, but to truly understand and predict the behavior of materials, we need to bring them together. In lesson 1.5, we are going to do just that. We'll combine the first and second laws to drive and understand two incredibly important thermodynamic potentials, Helmholtz free energy, and most importantly for materials science, Gibbs free energy. We'll also briefly touch upon Maxwell relations and then dive deep into their profound applications in materials systems, particularly in the context of phase diagrams and chemical potential. Let's start by combining the first and second laws. Recall the first law for a closed system. du equals dq minus dw. For a reversible process, we know that dq of rev equals tds from the definition of entropy, and dw rev equals pdv for pressure volume work. Substituting these into the first law, we get the fundamental thermodynamic relation for a reversible process, which is du equals tds minus pdv. This equation is incredibly powerful because it relates changes in internal energy to changes in entropy, temperature, pressure, and volume. It's valid for any reversible process and can be extended to irreversible process as well, as U, S, P, T, and V are all state functions. From this fundamental relation, we can derive other thermodynamic potentials that are more convenient for specific conditions. The first one is Helmholtz free energy. It is defined as A equals U minus Ts, where U is internal energy, T is absolute temperature, and S is entropy. Helmholtz free energy is particularly useful for processes occurring at constant temperature and constant volume. Under these conditions, the change in Helmholtz free energy delta A represents the maximum amount of work that can be extracted from a system. The criterion for spontaneity at constant T and V is when delta A is less than 0, the process is spontaneous. When delta A is greater than 0, the process is non-spontaneous. And when delta A equals 0, the system is at equilibrium. Pay attention, crucial for solving problems further. You have to get it right. While important in some contexts, Helmholtz free energy is less commonly used in materials science compared to Gibbs free energy because most metallurgical and materials processes occur at constant pressure, not constant volume. Now let's introduce the most important thermodynamic potential for materials scientists, Gibbs free energy. It's defined as G equals H minus Ts, where H is enthalpy, T is absolute temperature, and S is entropy. Gibbs free energy is the ultimate criterion for spontaneity for processes occurring at constant temperature and constant pressure, which, as we discussed, are the most common conditions in materials processing. The change in Gibbs free energy delta G represents the maximum amount of non-PV, non-pressure volume work that can be extracted from a system. More importantly, it tells us about spontaneity. Let's zero in on this next part. It's a key concept for every problem we'll tackle. When delta G is less than 0, the process is spontaneous, thermodynamically favorable. This means the reaction or transformation will proceed naturally. When delta G is greater than 0, the process is non-spontaneous, thermodynamically unfavorable. This means the reaction will not proceed on its own under these conditions. When delta G equals 0, the system is at equilibrium. There is no net driving force for change. The relationship delta G equals delta H minus T delta S is incredibly powerful. It shows that spontaneity is a balance between the tendency to minimize enthalpy exothermic reactions and the tendency to maximize entropy increased disorder. At low temperatures, delta H often dominates, while at high temperatures, the T delta S term becomes more significant. From our fundamental relation, du equals Tds minus Pdv and similar expressions for dH, dA, and dg, we can derive a set of important relationships known as Maxwell relations. These relations connect partial derivatives of thermodynamic properties and are extremely useful for relating measurable quantities to those that are harder to measure directly. For example, from dg equals vdp minus sdt, we can derive partial derivative of t with respect to v at constant s equals negative partial of p with respect to s at constant v. These relations are powerful tools for thermodynamic analysis, allowing us to calculate changes in one property from measurements of another. Now, let's see why Gibbs free energy is so central to materials science. First, phase equilibria and phase diagrams. Phase diagrams are maps that show the stable phases of a material system as a function of temperature, pressure, and composition. The lines and regions on a phase diagram represents conditions where the Gibbs free energy of the different phases are equal, indicating equilibrium. For example, in a simple binary alloy system, the common tangent construction on a Gibbs free energy with composition curve allows us to predict the equilibrium compositions of two coexisting phases. Understanding delta G for different phases is the thermodynamic basis for constructing and interpreting these essential diagrams. For multi-component systems, we introduced the concept of chemical potential μ. It's defined as the change in Gibbs free energy of a system when 1 mole of a component is added to it, while keeping temperature, pressure, and the amounts of other components constant. This formula defines chemical potential of a component I in a mixture, which is mu I is equal to partial derivative of G with respect to n sub I at constant T, P, and n sub J not equal to I. Chemical potential is the driving force for mass transfer. Just as heat flows from high to low temperature and mechanical work is done from high to low pressure, a species will move from regions of high chemical potential to regions of low chemical potential until equilibrium is reached. That is, chemical potential is uniform throughout the system. This is fundamental to understanding diffusion in materials. The third application of Gibbs free energy to be mentioned here is driving force for transformations. Any process in a material, whether it's a phase transformation like austenite transforming to perlite in a steel, a chemical reaction like oxidation, or the dissolution of a precipitate, occurs because there is a negative change in Gibbs free energy. Delta G is less than 0. The magnitude of this negative delta G represents the thermodynamic driving force for the transformation. A larger negative delta G means a stronger driving force. In summary, By combining the first and second laws, we've derived the Helmholtz and, more importantly, the Gibbs free energy. Gibbs free energy, G equals H minus Ts, is the crucial thermodynamic potential for understanding spontaneity and equilibrium at constant temperature and pressure. It serves as the bedrock for interpreting and constructing phase diagrams, understanding chemical potential as a driving force for mass transfer, quantifying the driving force for all kinds of transformations in materials. To delve deeper into these crucial concepts, I strongly recommend this reference. This concludes our first module on the fundamental thermodynamic laws and their applications. In our next module, we'll shift our focus to availability and efficiency, building upon these foundational principles to understand how efficiently energy is utilized in materials processes. Don't forget to like this video, subscribe to the channel, and hit that notification bell so you don't miss any future lessons. If you have any questions, drop them in the comments below. Thanks for watching, and I'll see you in the next lesson. Alright everyone, we've now reached a significant milestone in our course, the conclusion of Module 1, Fundamental Thermodynamic Laws and their applications. We've covered a lot of ground establishing the core principles that govern energy and spontaneity in materials systems. Let's quickly recap the key takeaways from Module 1. We started with the first law of thermodynamics, which is all about the conservation of energy. Remember, energy cannot be created or destroyed, only transformed. We introduced the equation delta U equals Q minus W and saw how enthalpy becomes a convenient measure of heat changes in constant pressure processes, which are very common in materials engineering. Then we moved to the profound second law of thermodynamics. This law introduced us to entropy, a fundamental concept representing disorder or energy dispersal. The key takeaway here is that for any spontaneous process, the total entropy of the universe always increases. This law tells us the direction of natural processes. We briefly covered the third law of thermodynamics, which provides a crucial reference point. The entropy of a perfect crystalline substance is zero at absolute zero temperature. This allows us to determine absolute entropy values, which are essential for comprehensive thermodynamic calculations. Finally, we brought it all together with the powerful free energy functions. We briefly looked at Helmholtz free energy, but most importantly, we focused on Gibbs free energy. This is defined as G equals H minus Ts and is the ultimate criterion for spontaneity and equilibrium in material system at constant temperature and pressure. The relationship delta G equals delta H minus T delta S shows the critical balance between enthalpy and entropy in driving transformations. And we saw the immense applications of these laws. They are the bedrock for understanding and interpreting phase diagrams, for comprehending chemical potential as the driving force for mass transfer, and for quantifying the driving force for all kinds of transformations in materials, from chemical reactions to phase changes. So, with this strong foundation in the fundamental laws of thermodynamics, we are now perfectly positioned to move into our next module. Module 2, Availability and Efficiency. In this upcoming section, we will build directly on these principles to explore the concept of availability or exergy, which tells us the maximum useful work we can extract from a system. and how to quantify and improve the efficiency of materials processes, moving beyond simple energy balance to a more insightful thermodynamic analysis. This will show us how these fundamental laws translate into practical implications for energy utilization and sustainability in materials engineering. Thank you for joining me through this foundational module. I encourage you to revisit any concepts that felt challenging, as a solid grasp of these laws is crucial for everything that follows. Don't forget to like this video, subscribe to the channel, and hit that notification bell so you don't miss our next module. If you have any questions, please leave them in the comments below. See you in Module 2.